Welcome to today's webinar, Statistical Engineering, what it is not, and how it relates to other disciplines, a member's perspective. First of all, I'd like to start off by thanking the organizers for this webinar. So thank you to Pete Parker, who was the primary organizer for setting up this webinar, and also to Jeff Vining and Sherry Craver. The format for today's webinar will be that we will have three speakers give two presentations, and then that will be followed by a discussion from three different discussants. Following the discussants, we will have a panel discussion, and we will lead off the panel discussion by allowing the three speakers to respond to the discussants, and then we will open up to questions from the audience. Our first speaker is Caleb King, who will be giving a talk entitled Statistical Engineering, Finding Our Identity. Dr. Caleb King is a research statistician developer for the Design of Experiments platform in the JUMP software. Prior to working at JUMP, he was a statistical scientist at Sandia National Laboratories for 3 years. He received his MS and PhD in statistics from Virginia Tech. Welcome, Caleb.
All right, thank you, Jennifer. And thanks everyone for attending my talk. And hopefully there'll be a lot of questions that you consider from this. So we'll be providing definitely a lot of questions and topics for thought. Speaking of questions, I'd like to start off with one. Let's see, there we are. Who are we exactly? Now, before you start getting all metaphysical and thinking about how that pertains to yourself, so I mean, who are we exactly in relation to ISEA and statistical engineering? This is a question I kind of found myself asking after the second summit, as I felt there was still a bit of lingering confusion about what this new field was. What exactly was its purpose? What was it trying to do? So as I typically do, when I came back, I discussed things with my wife, told her how the summit went. And as I tried to explain my thoughts on what statistical engineering was, she too became confused, either because I wasn't good at discussing it or, we both were confused about things. So this led to several evening discussions over the course of several weeks of us trying to wrestle with what did we think the sources of confusion might be. And once we identified them, what might be some potential solutions to overcoming those sources of confusion? So ultimately, that all led to this presentation here. And if you're worried about my wife and I's extracurricular like evening activities, that our hobbies might be a little off, don't worry. We now have a 3-month-old daughter that takes care of that. So ultimately, what we did is we ended up converging on what we believe were the two primary sources of confusion, and that is, how does statistical engineering relate to statistics, and how does it relate to other analytic disciplines? So we'll be kind of talking about each of those. But before we get into that, we obviously need to say, what do we currently say statistical engineering is? And for that, we'll go to the handbook, where we have the definition as given here. Now, let's break this down a little bit. This field is supposed to be about the study of the systematic integration of statistical concepts, methods, and tools. So if the name itself didn't give it away, this field is inherently tied to the field of statistics. Our question is, what is the exact nature of this relationship in light of how statistics could be defined? We also note here in the definition that it's intended to work with other relevant disciplines. So it's meant to be multidisciplinary, at least that's how it reads. So what exactly is the nature of this relationship to these other relevant disciplines? And what are some of these other relevant disciplines? So we'll kind of discuss that as well. I'll throw up another topic real quick. We won't really discuss it, but the point of this field is to solve important problems sustainably according to the definition. Now, typically the way we define that is these problems are complex and unstructured, so they're more difficult. I probably prefer that term over something like important problems, because that begs questions of what makes something important, who gets to determine importance. If a problem is not deemed important, does that mean we don't handle it? I don't think so. I don't think that's the case, but just something to consider in terms of the wording of the definition. But we won't go into that. We'll talk about the first two. And speaking of which, let's transition into the first one. How does statistical engineering relate to statistics? What's the area of confusion there? Now, in the handbook, that relationship is compared to that between chemistry and chemical engineering. And when we read that, this brought up in our minds the relationship between a scientific discipline and an engineering one, which then of course begs the question, what makes a discipline a science and what makes it an engineering discipline? Well, as any good researcher does, we went, excuse me, drum roll please, we went to Google, of course. Where else would we find the answers? So what we did is we looked up online and tried to find various definitions of each branch. So for a scientific discipline, here's kind of what we came across. Now we've highlighted some key terms that we believe gets at the core idea, and that is that a scientific discipline is one that systematically acquires knowledge about a subject. So it's all about knowledge acquisition. Compare that to an engineering discipline, which, as we peruse these definitions here, we've again highlighted a couple terms, which we believe gets to the core idea. That is that an engineering discipline is one that practically applies that scientific knowledge to solve problems. So we have knowledge acquisition in science, and we have a knowledge application in engineering. Now, to help illustrate that, we'll have two individuals here. Let's talk to the person on the left first. We ask them, what do you do? Well, they say, I am a chemist. Hello, chemist. What do you do, chemist? And the chemist might reply, I research matter. What makes up matter? How do substances transform from one form into another? They study molecules, atoms, so they basically study what makes stuff. How is matter comprised and how does it transform from one form into another? So they're all about acquiring knowledge about matter and the properties of matter. Now the person on the right, we asked them, you can probably guess who it is. They're a chemical engineer. Hello, chemical engineer, what do you do? So the chemical engineer might reply, I take my knowledge of chemistry and I apply it to certain industrial processes. Maybe I look into how certain properties of materials and say, how could we use this in industry? Maybe I could consider improving upon the material in some way. Maybe I could create a new material that addresses my problems. Maybe as I study how substances transform from one form into another, I can use my understanding of chemistry to say, can I make that more energy efficient, say? So it's this idea of the chemist is acquiring knowledge about matter, and then the chemical engineer is taking that knowledge and then trying to use it to solve problems out in the field. Okay, now to help us going forward, we'll have this nice handy dandy table. Again, just to summarize, this science, so a scientific discipline is what we're saying has systematically acquires knowledge, so it's all about knowledge acquisition. An engineering discipline is about that application of that knowledge. So chemistry is the science, chemical engineering is the engineering. They fit very nicely. Now the question is, what about statisticians? So as you can imagine, we have here a statistician, and we ask our friendly neighborhood statistician, what do you do? And they might reply, well, I research ways on how to extract information from data in the presence of uncertainty. So I might try and develop new analytical techniques to extract that information. I might research how to maybe even set up experimental designs to get that information more efficiently. So I'm all about finding new methods to get that information. Now, someone in the audience might say, hey, that pretty well describes what I do. But some of you might say, well, actually, I too am a statistician, but I'm more on the application side. So I actually take those methods and I apply them. I work with customers. We work with them to collect the data. So I might collect some of those experimental designs. We'll pick a good one. We'll try and implement it. And then once we get the data, we'll use some of those analytical techniques to extract the information. So I'm more on applying those techniques. So as what we see here is we have this strange hybrid behavior going on with a statistician. And you may have statisticians that are more on one side than the other. You might have statisticians who are a nice balance of both. So this is what we believe is the source of the confusion between the relationship between statistical engineering and statistics. Namely, we don't really know how to categorize statistics very well. Is it a science? Is it an engineering discipline? Where should it go? So let's see what happens as we explore different placement options. So where you think statistics fits in, this will inform what questions you're going to be asking about statistical engineering. So let's explore some of that. Let's say, to start off with, that maybe you lean more that statistics is more like an engineering discipline. It's all about the application of those analytical techniques. It's about working with the customers to extract the information that they need from the data, to help them design the experiment to get that information. So it's all about the application. Okay, well, if your thinking is that way, then where is the knowledge that you're pulling off from? Who's in charge of that? Is it probability theory maybe? Is it some other branch of mathematics that deals with that? And so that's one question. Another question that kind of comes up is, if this is the way you think it's supposed to be, then you're probably thinking, why do we need statistical engineering? I mean, we are essentially already an engineering type discipline. Why do we need another one? What, don't we just need better training as statisticians? Is that essentially what you're saying? So you can kind of see where a lot of people, and what I've seen, at least the initial way I was thinking about it, this is kind of the question I was asking: why do we need a new discipline if this is the way it's supposed to be? Now, maybe you might think differently. You might say, you know what, I'm happy and fine with us being this weird hybrid discipline. Yes, we can be science and engineering. I like living in this nice little tension. So I'm fine with that. I'm comfortable with that. Again, the question is, then where does statistical engineering fit in? Again, we're kind of in the same boat as the first case. Why do we need this new discipline if we already handle it? So if this is the way you think of statistics, this is where you can get that confusion coming from. The third case is saying, well, maybe you think statistics is more of actually the science end. That statistics is about the research into those methods. It's about researching to create new analytic methods, create new experimental designs. And if that's the way you think, then you're probably more comfortable with the idea of statistical engineering, because it's like, okay, that's the application of statistics, the science of gathering information from there. So in this case, you're pretty comfortable with that. But the questions you might be asking then might be, okay, well, if that's true, then are you basically saying that we might need to do some rebranding of ourselves? So, if I'm currently a statistician who does consulting work, does that mean I should be calling myself a statistical engineer going forward? I know there are a couple people who have actually been doing this. And maybe if you're in statistics, or you consider yourself a mathematical statistician or statistical scientist, maybe you just need to call yourself a statistician, because that's what you do. That's the science part. So again, these are what we believe are the three different ways of looking at it. And if this is the correct way to think about it, then essentially what we're saying is, well, we kind of need to adjust how statistics is viewed. We need to make it focus more on the science end so that we have a nice place for statistical engineering. The question then is this what we want for the field? Now let's pivot. Let's move to how statistical engineering might relate to these other analytics disciplines. And to start off, I think the best way to understand what those other relevant disciplines are is there's been a diagram going around, originally designed by Dr. Vining. I say originally here because, as you'll see, we spruced it up a tad bit. You can thank my wife for that. It's one of her great talents. But the reason we like this diagram is it clearly shows what all other fields we're looking to draw on, what other tools we're looking and skills we're looking to draw on to create this thing we're calling statistical engineering, and how it leads to the better solutions that we hope for. Now, let's focus a bit on the tools at the bottom. So we've got these non-analytic fields such as behavioral psychology and such, and these might be to help us interact with other individuals to get these solutions, these sustainable solutions. We have what here's called industrial analytic fields. You can think of it as, you could replace with business analytic fields or the medical analytic fields, essentially. Basically, what are the areas that you might be working in that you might need a little bit of subject matter expertise in? And then what we're concerned with is the nature of this relationship. What about these other analytic fields that are out there? Now, one thing is that statistical engineering is claiming to be tool agnostic, that it doesn't matter what tools you use. So it's fine with using tools from other areas. How exactly is that supposed to work? And so in our discussions, we kind of, again, leaned on what we think are two different approaches to that. The first is what we'll call statistical engineering as collaboration. Essentially, this idea says that statistical engineering is coming into a whole field of other analytic disciplines. We're just coming in as yet another one. And we have our own advantages and disadvantages, and the other fields have their own, disciplines also have their own advantages and disadvantages. We have our own tools, they have their tools. But again, since our goal is to get sustainable solutions, we're coming in not to compete, but to collaborate. we're coming in to say, you might have a tool that really that gives us a sustainable solution we want. So we'd like to borrow the tool from you, essentially saying that once we take that tool, we're assigning ownership of the tool to the other discipline. If that's still a little confusing, let's use an illustration. And in fact, a great illustration came from this very webinar series. If you were in the last session, last month, you saw this talk on statistical engineering and machine learning case study to predict student success or failure. The reason we believe this is a great illustration, so it presented 3 different methods, 2 of which were categorized as statistical, one which was a machine learning technique, a neural network. Notice that the statistical methods, essentially through the title, are being categorized under statistical engineering, and the neural network approach is being categorized as machine learning. We're borrowing the neural network tool, but we're assigning ownership to the machine learning area. If you still don't understand, think of it this way. What if instead the talk had been titled Statistical Engineering, a case study to predict student success or failure? And then it presented 3 statistical engineering methods. Notice in that case, all the methods are considered a statistical engineering tool. This is an example of what we'd call statistical engineering as consolidation. The idea here being that statistical engineering is coming out and saying, we have all these analytic disciplines out there. They have all their own tool sets. They're kind of all little stovepipes maybe into their own organizations. But we believe if we were to combine them all under one field, perhaps that we'd be in a much better position to solve these complex problems because we wouldn't have to work with convincing other disciplines to unite together to solve the problem. So maybe statistical engineering is some attempt to unite all of these into one overarching discipline. Everybody then simply becomes a specialty group. So if you're a data scientist, well, that's a special type of statistical engineer. You just have a particular tool set you like to focus on. Maybe you might specialize in more than one branch. If this is the intended idea, then it does bring up a question, one that has come up before. Is it fair to call this field statistical engineering? Because it clearly favors one discipline, statistics, over everybody else. Wouldn't something more general be appropriate if this is the intent? Okay, so we presented what we believe are the 2 sources of confusion and tried to explain where that confusion might be coming from. So now let's talk about what are some ways that we might be able to clear up that confusion. Again, I'll remind you that this is kind of our opinion on it. We're just trying to generate questions and topics of discussion for you to think about. So what do we want to be? Let's start with what we all can agree on. And that is this idea that our current practitioners seem ill-equipped to handle complex problems. So that's what led to the rise of statistical engineering. We need to give them better training. We need to make sure they have the necessary skills to handle those complex problems going out. We all agree this is what's needed. We definitely agree on that. But where we might disagree is what exactly is the end goal of statistical engineering, and how we answer that determines how we get there. So again, the original vision was just to better prepare students for complex problems. Is that still the sole vision, or has it expanded to include other aspects? And again, we see at least 3 options going forward. Again, there might be more options. The best option might be a hybrid of these. We're just presenting what we believe are our 3 possible options. Option number 1, we call courses only. The idea behind this is it's kind of getting at that idea of, statistics is this weird hybrid of science and engineering, and maybe we're okay with that. So if we are okay with that, then under that perspective, we should just really focus on creating better coursework that helps our students be better prepared. We should be fine including techniques from other disciplines. We can borrow and collaborate with them as we need to, but we're still going to be statisticians doing this. We just need better training. So the advantages of this would be that it's a lot easier to accomplish than creating a new field, and we can quickly achieve the idea of getting better prepared statisticians. Now, of course, the cons are we're not creating a new discipline under this option. There really is no major change to the status quo, other than you need better courses. Option number 2, what we're calling split statistics. Under this one, the idea is that, yes, we recognize that currently statistics is this weird hybrid. Maybe it would be better if we did kind of split it up and refine it, maybe made statistics be more of the science discipline, have more of a science focus, and let statistical engineering be a new discipline that covers the application. That way, the statisticians who are currently doing research can be more focused on that end, and those that want to do more of the application, okay, now we have an entire discipline to help you accomplish that, maybe better than we currently can. And again, the idea is we're coming in as collaborators. So we're happy to take techniques from other analytics disciplines as we need, so long as we ascribe proper ownership. And of course, the advantage of this is that it clears up any confusion between statistics and statistical engineering. We have placed them into specific roles. We also get the advantage of being able to follow in the footsteps of people who've gone before us. So that chemistry and chemical engineering example, based on our brief research, it seemed it had a similar look in that chemical engineering kind of came out of chemistry, and we get to follow in those footsteps. The next, now the downsides to this, let me get this going again, sorry, is we're kind of creating a new discipline at the expense of the old one. This isn't necessarily a big con because statistics will still be around. We're not getting rid of it, of course. We're just having to restructure it a bit. I guess the bigger difficulty will be that you'll have to convince a lot of people that this is the way to go. That if you're a practicing statistician, maybe you do, if you're more into consulting, maybe you do need to rebrand yourself as a statistical engineer. And maybe that might need to require a little more training. The final option is what we're calling level up. And the idea behind this is we see some differences amongst the analytics disciplines, but we also see a lot they have in common. And ultimately, we believe that with our powers combined, we could solve a great ton of complex problems that we couldn't before. Think of it as like an analytical Avengers, if you will. So the idea would be, let's try and unite all these disciplines under one field, and let's give it a fair name. I propose analytical engineering here. There could be other names, but ultimately it's this idea of, let's combine the things together so that we're not having to work independently. We're not reinventing the wheel whenever a new discipline comes out. We're better off together than we are apart. The advantage of this is that we get to leverage a lot more tools because everybody's working much more closely now. Our discipline name doesn't favor one over the other. And we're also much more wide-reaching. We'd be able to solve a lot of problems that we probably couldn't on our own, or at least trying to collaborate. Now, the downside, of course, is that ISEA would have to change its name. Statistical engineering essentially would a name and definition change. And you've got quite the uphill battle because you're basically asking a lot of the folks in the other disciplines that, we believe this is a good idea. So you should you should unify, we should come together to do this. So that's definitely a lot of work. All right, so why does all this matter? Why talk about this? Why go through all this hassle presenting options and discussing sources of confusion? Ultimately, it's because we believe in the ideas behind the statistical engineering movement. As the paper that kind of introduced it said, it's an idea whose time has come. We're living in an increasingly data-driven world. We definitely need people who are much better prepared to handle complex problems than they are currently. What we're worried about is that we might be getting a little too far ahead. The illustration that I kind of think of is of building a house. And right now we're working on pouring the foundation. But there's also this kind of fear that maybe we're starting to put up walls, put up the frame and everything before the concrete has even set. And that could cause problems going forward. If we don't know who we are, if we don't resolve this confusion, how can we advertise it to others outside if we don't even know what exactly we're doing? So we want this to succeed. And so that's why we spent time to put this together. That's why we had all those evening discussions to try and identify what are the areas of confusion? What are some ways that we can try and clear up that confusion? Try and provide some thought-provoking questions, some topics of discussion that ultimately the ISEA leaders and members can come together and discuss and hopefully provide a more unified path forward. Now, hopefully I'm not too far over time. I do have a few more slides, just 2 more slides left. And that is, well, suppose you did ask us. Suppose we did say, if you asked us, what would you do? How would we approach this? Well, if you want our opinion, of the 3 options, The first one's completely out. We're well beyond that. You know, this has gone far beyond just courses only. We know we need more than that. It's far beyond that. Third option is also out, mainly because, you know, it sounds great in theory, but we are nowhere near able to do that just yet. That's something further down the road that could be considered by someone at that time. So ultimately, we lean kind of this idea of the splitting of statistics. We believe that this best represents the desire to make better statistical practitioners. It's something that correlates to what we're kind of trying to do now. And how exactly would we do that? Well, of course, my wife's a project manager, so of course we have a solution. The first step is, of course, we need to redefine our definition. So here's some examples of what that might look like. Again, I'm not proposing a formal definition, just an example. And ultimately, we have to advertise that, you know, we have to kind of have this subtle split. Statistical engineering will be on the application side. Statistics will be on more of the research, the knowledge acquisition side. So as we're promoting this, we're also trying to accumulate and determine, okay, what should a statistical engineer know? What are the skill sets they need? As we reach out to the wide range of industries, as we advertise this, we're going to ask the statisticians who work there, what do you wish you would have known? We're going to ask the people they work for, what do you wish your statisticians would have known? And we're going to compile that and document that in one place. Once we have that list, then we can kind of map out this ideal program. In this case, we consider it a master's program. What would it kind of look like? Essentially, now that we know what they need to know, where do they get that knowledge? What classes would students need to take? What kind of experiences would they need to have that? And then once you have that, you can set up a course. The reason we're sticking with just a course is that's kind of how chemical engineering came about. It started off as a single course. The idea is kind of that the course is a way to get our foot in the door. And then it also serves as kind of the guinea pig. You get to see what works, what doesn't. You can relate it back to your ideal master's program and kind of say, you know, what are the topics that I might need? Do I bring in guest speakers, or is it, you know, they're going to have to take another class? So as you do that, you're going to continue with this course over time. You'll be able to refine it, so forth. You'll recognize what other courses you need. And after that time, you'll finally be able to have a conversation with universities about setting up a program because you're better suited to understand what you actually need. And again, throughout all of this, you're continuing to advertise the idea of statistical engineering, how it relates to statistics, this new idea of statistics, maybe pseudo new idea. And ultimately, we hope that by doing this, you'll be able to not sit back and watch because you're going to be busy, but you'll be able to watch as the discipline quickly grows and forms, better prepared. So that's all. Thank you for your time and consideration.
Thank you, Caleb. We are actually going to hold questions until the panel discussion. So if you have questions, please type them into either your chat box or the questions window. Our next talk is going to be given by Will Guthrie and Dennis Leber, entitled Statistical Engineering, We Are Not Alone. William F. Guthrie received a BA degree in mathematics from Case Western Reserve University in Cleveland, Ohio in 1987, and an MS degree in statistics from The Ohio State University in Columbus, Ohio in 1990. He is a fellow of the American Statistical Association. He worked as a mathematical statistician in the Statistical Engineering Division at the National Institute of Standards and Technology in Gaithersburg, Maryland from 1989 to 2014. In 2015, he became the chief of the Statistical Engineering Division. Dennis D. Leber is a mathematical statistician at the National Institute of Standards and Technology. In his collaborative role in NIST's Statistical Engineering Division, Dennis provides leadership and guidance in problem formulation, experiment design, and statistical analysis for physical science research to the scientists and engineers at NIST and other federal agencies. Dennis holds an MS degree in statistics from Rutgers University and a PhD in mechanical engineering from the University of Maryland. Welcome, Will and Dennis.
Great. Well, thank you very much, Jennifer. Enjoyed Caleb's talk. There's some overlap I see clearly between how we're thinking about things. So that's interesting and good to see, I guess. I don't know. We'll see where we all end up with this. It's an adventure as we go through it. So let's go ahead and get started. If we could have the next slide, please. So I want to give you first a little bit of background on what we do in the NIST Statistical Engineering Division. You see that we have statistical engineering right in our name, and it seems from some research that was done in the founding of statistical engineering, the discipline, and ISEA, that it's possible our founder, Churchill Eisenhart, coined the term statistical engineering back in the late 40s and was the first to publish it in 1950. But there's a little difference, we believe, between how he was thinking about it and how it's being used to define this new discipline that we're all interested in. It seems that Churchill was thinking about engineering statistics, the application of statistical methods to engineering, other engineering problems. And that is a lot of what we do in our division, but we increasingly do what I think of as the discipline of statistical engineering as well. So you see our mission there is to develop and apply statistical methods that underpin the advancement of measurement science and technology. So everything we do is driven by measurement science and technology. And of course, you know, we're a group of statisticians, we're all about doing statistical things, but we realize we've got to go beyond that sometimes as well. Just the statistics leaves us too narrow, and someone's got to be looking at the bigger picture. And the way we achieve that at NIST often is through collaborative research. This is what we do day in and day out. All the folks in our group are working with NIST scientists and engineers to solve problems related to measurement. And I've got a few examples here that I think are good statistical engineering style examples of things that we have been doing recently. One project we're working on that's very exciting is helping chemists and physicists develop a genetic sensor biofoundry. The goal is to use the robots that you see in the first photograph there inside that glass enclosed room to set up and run experiments to turn cells into measurement devices that could be in someone's body. So if you need a cell that responds to a lack or an excess of sugar in your blood, a cell could be injected, and this cell could live in your body and would make a signal when the sugar is too high or too low, or in the presence of other biological chemicals related to disease or something else, and then action could be taken. So these robots are meant to do fully autonomous experiments. We start off with a goal in mind, and they start off at a with some original cells, and they run experiments automatically to reach and to push these cells to become good sensors. Another project is data-driven real-time control of Navy calibration logistics. There are thousands of tools on aircraft carriers and in the aircraft that are on those carriers. They all are, and measurement instruments, they all need calibration. And when they're out at sea, they can't really do that very well. They've had sort of a human-driven expert way of doing that. But we'd like to use knowledge about which labs have most capacity. Why are you sending something to a lab you've had good luck with in the past, but is very busy, when there's another lab maybe closer by with more capacity to do your calibration more quickly. And then finally, we've done work on estimation of extreme wind speed maps to reduce building costs across the nation. So here we're going to implement something in the building codes across the nation that will allow us to set standards that relate to the region you need to have your building in, as opposed to just having a set nationwide standard that has to be the max across the board. You see from the map, wind speeds are higher in the center of the country than on the coasts generally. And so we want to take advantage of that to make our world more efficient. Next slide, please. These are big problems, as you can see. So we have a colleague, Jim Philibin, who's been with us. He's just completed his 51st year in our division, and he's I think our model statistical engineer in some ways, and he's got a lot of tools he's developed over the years that he uses to organize his own thoughts, to sort of define what's going on, and to communicate and extract information from the people he works with. So many times he likes to describe how expert solutions are relied upon. So if you want to move one step forward, please, Dennis. Yes. So there's a problem defined, you turn to an expert, that expert gives you an opinion, and you move on to a solution. But of course, as statisticians, we really like the data-driven approach. And so this is the alternative path. And then Jim would explain this to his collaborators, show where design of experiments fits in, where statistics fits in, pre and post data. He would talk about where do you define the population of interest? That's over on the problem side, I've even before the design of experiments. Where do you pick your statistical tools, think about their assumptions, think about the nature of the outputs they have. Do they give you the sustainable answer you need? So he's also got tools for identifying factors and setting up experiments, and for analyzing experiments in standardized ways that he likes to use. So I think he is building a discipline of statistical engineering all on his own in some ways, and we want to do the same thing and broaden it out. So next slide, please. But that gets us thinking, after this, we sort of started thinking along the lines of, are we really capturing everything? At the last ISEA summit, and it makes us think about, what are our neighbors doing and what is ISEA talking about? So here, I won't stay too long on this slide because I think people are familiar with this. Here's what ISEA has laid out as its definitions of statistical engineering, and their hallmarks of the problem are down there. We see it very much as a problem strategy results-centered discipline with large, complex, unstructured problems as the target. And the picture that you see down there in the lower right is very reminiscent to me of the graphic that our colleague Jim Philibin uses. It shows the phases of the large, complex, unstructured problem solution, the phases that large, complex, unstructured problems go through when they're being solved. And it's very much like the things Jim shows, and the tools fit in different slots there, etc. So let's go on to, please. So now, thinking about how our neighbors at NIST do things, we have the Applied and Computational Mathematics division next door to us, figuratively now. It used to be literally, which was very nice. And their role, like SED, is to provide leadership in the use of applied and computational mathematics to solve problems. And they often engage in collaborative research with NIST scientists and engineers as well. And they have problems that look to me much like statistical engineering problems in a lot of ways. For example, they're working on metrology for microfluidics. So the picture you see there is a whole series of microfluidic chemical test chambers, and they are learning how to deliver very small, very precise amounts of reagents into those reacting chambers, so they can do a whole series of high throughput experiments to optimize various chemical techniques. And they can do things like control flow rates down to maybe 10 nanoliters per minute with a plus or minus 5% uncertainty with the methods they've developed. But their tools are a little different than ours. For example, in the microfluidics, they're using partial differential equations as their model instead of the kinds of models we might use as statisticians. We've got modeling biofets or biological field effect transistors to enable personalized medicine. This is a more of an electronic approach to doing diagnostic measurements than compared to the next one I'm going to talk about. But how to extract the information from that. They're using complex mathematical tools to do that. It hasn't been done quantitatively before, and they're bringing quantitative results to this area using, I think, stochastic differential equations in this case. And then finally, another example they have is they've got a simulation platform for human body communication. Again, a medical diagnostics thing. They want to have different parts of a medical sensors talking to one another, sending the communication literally through the body. And so you might have a probe inside you and some sort of readout in another place. They want to have that communication between those things happen wirelessly, but not using radio frequencies. And so they've got finite element simulations of how the signal propagates through the body. Those all seem like large, complex, and unstructured problems to me, and yet they're not exactly what we do. So next slide, please. So this is where we see a little bit of a, confusion, as Caleb put it nicely, I think, about what is statistical engineering and where are its boundaries. The mission and activities of SED and ACMD, the mathematics division, are similar, but they're not identical. And yet they both align, in my mind, with statistical engineering, somewhat imperfectly, but definitely aligned. SED staff are very aware of ISEA and the idea of, the split between theoretical and applied statistics, but the mathematics staff don't know anything about statistical engineering, I would wager. So it makes us think, if our near neighbor, is doing statistical engineering potentially, but is not aware of ISEA, how often are we missing out? How often is this situation replicated? And who and what are we missing? So with that, I think, as I mentioned, this came up in the last year's ISEA Summit. Dennis was the person who sort of got the ball rolling, for me at least. And I'm going to turn the floor over to him to talk a little more about his thoughts on this. Thanks.
Thank you, Will. And I'd like to thank Pete and Jennifer and all the organizers here for inviting us today. This is a very exciting time to have the opportunity to help shape and form some of these definitions, perhaps in this discipline that will live on for years to come. In my introduction, it was noted that I am trained in both statistics as well as engineering. In addition to, I've been a longtime member of the Statistical Engineering Division at NIST. So of course, when I heard of this organization, ISEA, that has the word statistical and engineering in the title, I got excited. That problem-solving framework that Jim Philbin has come up with, that kind of diamond that has data, in the middle, and he describes everything prior to data as design of experiments, problem formulation, et cetera, and everything after is statistical analysis. I always found myself enjoying the stuff on the left-hand side, the problem formulation, the working with the collaborators and the team to really define the problem well, to make sure we have a sound methodology for collecting our data before we go and try to analyze it and draw conclusions. Because we all know as statisticians, garbage in, garbage out. If we get the wrong data, our conclusions are not worthwhile. So this idea of ISEA was very exciting to me. What you're looking at there on the screen is not the ISEA website, but perhaps it could be, right? This idea that we want to work on big problems where we save lives, we save money, and we do all this by solving problems. We might consider that statistical engineering is this process that allows organizations to turn complex challenges into substantial opportunities by transforming data into information and information into insights. So perhaps this is maybe not perfect, but we could go there. But who else is doing work like this? I'm going to first turn to this organization, Institute for Industrial and Systems Engineers. On the ISEA homepage, there's a link to a talk that Roger Hurl gave, this very nice collection of discussions that Jump puts together called Analytically Speaking. And in that discussion that Roger had, he talked about this idea of improvement. Statistical engineering is meant to drive improvement. Well, when I think about improvement, I think about industrial engineers. And from the Industrial and Systems Engineering website, they use this definition that industrial and systems engineers seek to make things better. There's that idea of improvement. They do this by solving complex problems. That's their common objective. I see it also draws knowledge from a vast array of disciplines: mathematical, physical, and social sciences. I think that's attractive to ISEA, right? A very diverse set of disciplines here. And the mission statement of ISEA, of IISE, I think fits nicely with what ISEA is seeking to do. We serve those who solve complex and critical problems of the world. This Institute for Industrial and Systems Engineers is a very large organization. It has approximately 50,000 members worldwide. I'd also like to note quickly here that Jeff Vining gave a presentation recently about his first pass at creating a statistical engineering course at Virginia Tech. And in that first pass, he had 8 students. 6 of those 8 students were industrial engineers. And that does not surprise me. This idea of statistical engineering is about solving complex, unstructured problems, and I believe industrial engineers are certainly a group of people who do that. The Institute for Industrial and Systems Engineers publishes this body of knowledge, and I display this just to show the different areas that this organization works in, and how it is relevant to what ISEA is trying to accomplish. They look at measurement, OR and analysis, engineering management, so information engineering. So there's a lot of the same, there's a large overlap with what the Institute of Industrial Systems Engineers are doing to what ISEA is going after. Now I come back to this this mock-up of what a web page might look like for ISEA, and and I offered this as this might be ISEA's web page, but this is not ISEA's web page. In fact, this is Inform's web page, the Institute for Operations Research and Management Science. This is exactly what they aim to do: save lives, save money by solving problems. And it's not statistical engineering that is this process that it enables organizations to turn complex challenges into opportunities, but rather it's operations research and analytics. These are proven mathematical processes that do this. So Informs is, again, this organization that looks to improve things. They promote best practices. Again, I believe that is within the scope of what ISEA is seeking to do. They're looking to develop this statistical engineering discipline that promotes best practices for solving complex and unstructured problems. Well, if we look at what Informs is doing here, they're promoting best practices through operations research, management science, and analytics to improve operational processes and decision making. There's two very important definitions here that I think we need to consider that Informs provides. The first is operations research. Some of us may have a very traditional and old school thought of what operations research is. It's this idea of moving our soldiers around the battlefield to give us the largest advantage in perhaps a dispute. But operations research has really evolved in the most recent decades. And Informs now describes operations research, or defines operations research, to be the scientific process of transforming data into insights to make better decisions. And a new buzzword, this word of analytics is kind of a new recent buzzword that's come along, but Informs puts a nice definition on that. This idea of an application of scientific and mathematical methods to the study and analysis of problems involving complex systems. So those two definitions really, to me, fit well in with the ISEA mission. We're looking to use data to make better decisions and insights. We're looking to develop a discipline, a scientific discipline that studies how to solve problems, how to solve and analyze these complex problems. Down the bottom of this slide is some more words that I've taken from Inform's website. OR and analytics enables business leaders to address complex problems, to make more effective decisions based on data. Wow, that again sounds like a real close link to ISEA. Informs is not quite as large as the previous association that I discussed. It's at 12,500 members, but these members consist of data scientists, analytical professionals, machine learning, artificial intelligence. Again, all disciplines that I believe fall within the scope of what ISEA is trying to accomplish. To dive a little bit deeper into that, these are the various societies that Informs offers, and I think looking at this list quickly, we can see some places that are closely aligned with ISEA: applied probability, computing, decision analysis, information systems, optimization, and simulation. So Informs is really composed of the kind of people that ISEA could really benefit from. Informs also publishes a body of knowledge, an analytics body of knowledge. And I found this very interesting because in looking at the ISEA handbook, I see a lot of similarity between ISEA handbook and the Informs analytics body of knowledge. We begin with the idea of analytics, this idea of solving complex problems using data. There's a chapter here about data, collecting data. And then there's several chapters on, well, before we even get to that, there's a chapter on team building. How do we manage analytical talent and the team? We have several chapters in this body of knowledge here about the modeling and the analytical approaches to solving these complex problems. And then finally, they get to the deployment. How do we manage this moving forward? So this is, again, a lot of overlap I see with ISEA. So one of the major points of ISEA is looking at large, complex, this term important problems. I display on the screen here a dozen or so problems that are illustrated through informs, and there are many, many more that we can look at. There's often a lot of nice case studies behind the scenes with each one of these. These are large, complex, unstructured, important problems that the folks associated with informs are solving. Combating human trafficking, certainly large, complex, unstructured. A relevant one in today's world, predicting vaccine immunity. It's just, these are large, complex, unstructured problems. And we're going to dive down into a couple of these problems here a little bit deeper. But before I do, I wanted to I guess, recognize the Institute for Defense Analysis. They've begun putting on a really nice conference, I guess, called DataWorks. And at DataWorks, they have been recognizing the progress of ISEA, and I think it's only appropriate that we recognize IDA here. But IDA is also heavily involved in informs, and here's a nice article that David Hunter, who is a assistant director in the cost analysis and research division at IDA, wrote for informs. And in this, he notes that the IDA researchers, they're not focused, they don't have a hammer. They're not focused on an individual technique and trying to apply that hammer to every nail they find, but rather they study the problem. They figure out what are the most appropriate techniques to apply to those problems. So there is a lot of, they are certainly dealing with complex problems. They spend a lot of time and work and energy defining and studying that problem, and only then do they apply an appropriate technique to move forward. So with that, I'd like to jump into a couple of these case studies that Informs provides for us. The first one here is this idea of increasing bike share efficiency. So this company, Motivate, is the largest organizer of bike sharing applications across the country. They have operations in New York City, Washington, D.C., Chicago, and other major areas. They worked with Lyft and Uber and Cornell University in working through this problem of they need bicycles to be present where people need them and want them. And they also need docks to be available when the people get to where they're going. So if you think about someone commuting into a city, and a lot of people are taking bicycles on a nice spring day, the bicycles in the suburbs are going to get rented out very quickly in the morning. And when the people get downtown, they need a place to put them, so they need an empty dock. So those docks are going to fill up very quickly as the day progresses. So they want to balance that problem of always having bicycles available in the suburbs. They don't want them to be empty because I had to take the kids to a dentist appointment this morning, and I'm getting to my dock station at 10 o'clock and there's no bikes for me. How do I get to work today? The other issue that I've heard them mention is, everybody rides the bicycles into the city in the morning, and we get a thunderstorm coming through between 4 and 5 o'clock, 6 o'clock, and people are not riding those bikes back out to the suburbs in the afternoon. So now all of these docks in the city are full, and there's nowhere for anyone else to park bikes at these docks, and the docks in the suburbs are empty. So this is certainly a large problem. In 2019, there was almost 30 million rides taken between New York City, Chicago, and Washington, D.C. Very complex. This is, if you look at this kind of as an inventory management problem, but the customers are moving the inventory around all the time. We have this problem of managing both the bike availability and the dock availability. So there's two parts of this that's being managed. And there's a component of sensor data here. Motivate doesn't know when a customer shows up to a rack and there is no bike available for him. They're unaware of that. They're also unaware of the person who gets to a docking station and wants to put the bike away, but does not, so has to go find another docking station. So there's sensor data that they're dealing with. So there's a lot of complexity in this problem. They went about a number of solutions. They talked about reallocating their resources, moving these docking stations around. There's this idea of motorized rebalancing. It's this idea of a van or a trailer coming up and picking up bikes and moving them elsewhere. It's very expensive. It's very costly. Another solution they have is this idea of valets. A valet will stand at a full docking station, and they'll take the bikes and protect the bikes until a station opens up. But again, you have to pay another employee to stay there. And a final solution they offered was this idea of crowdsourcing, this idea of bike angels, where they encourage their customers to take bikes from certain places and drop them off at other places. So I haven't gotten very deep into this case study at all, but I do provide a link here that provides a really, really nice talk on this problem and this case study. The second case study here is this idea of Orion. This is UPS. I'm not going to go too deep here because I think I'm running a little bit short on time. But we all know UPS. They deliver many, many packages. Before this idea of Orion, this new optimized modern delivery operation system, the driver and a dispatch worker would spend hours in the morning loading trucks. The driver would then have a set route, and he would make changes on the fly depending on how he packaged his truck and whatnot. But UPS thought that there's a opportunity for improvement there. And a number of years ago, they took on this project. Very complex, very large. UPS is delivering 16 million packages a day, and that was pre-COVID. I can't even imagine what it is today. 55,000 drivers, 160 daily stops for each driver each day. So this was a large, complex, unstructured problem. Some of the solutions that came out of this resulted in 100 million miles and 10 million of fuel saved each year, which resulted in $4 million of savings, also reducing the carbon footprint by 100,000 metric tons per year. So again, very, very nice case study of a complex problem that you guys can go to the website that I offer down there that also gives another really nice video of this problem and solution. So with that, I'm also going to Informs does a great job of recognizing excellence in this area of operations research and analytics work. And two of the prizes that they offer are this Wagner Prize and the Edelman Prize. They have a nice video library of the presentations associated with each of those competitions each year, and I offer those links on the screen right here. And I believe that these are very, very nice examples of what we might consider statistical engineering. So I offer that for thought. And with that, I'll get to our final screen here where we're going to offer some questions for our panelists. I've talked about two communities here, the Institute for Industrial and Systems Engineers, as well as Informs, the Institute for Operations Research and Management Science, that I believe have a lot of commonality with what ISEA is trying to do. They are solving large, complex, unstructured problems. There's likely other organizations out there, perhaps from industrial psychology or economics or others, that also play in this large space. So the question number one here is, what can we learn from these communities, and should we consider partnership to achieve our mission? This kind of begs the question of, well, what are the qualifications of an engineer? This gets back a little bit to Caleb's talk, a very nice talk that he had here. Do you need to be a statistician to be a statistical engineer? Can you be an economist? Can you be an operations research analyst to be a statistical engineer? The second question here has to do with the case studies. I quickly presented case studies from Informs, and there are many, many, many available there. And I know that ISEA is currently trying to collect case studies to help formulate this discipline. But it begs the question, is a statistical engineering case study simply a large, complex, unstructured problem? And if that's the case, I believe Informs offers a lot of those case studies. Or do these case studies need to demonstrate that they use this established problem-solving theory of statistical engineering? Now, this is kind of a rhetorical question because I think we all know that statistical engineering is certainly in its infancy, and to suggest that there is a established problem-solving theory is maybe premature. But this also kind of there's a subtle component of this is, what do we consider as a statistical problem? Are these case studies that Informs offers, would we consider those statistical problems? What do we need to be considered a statistical problem? And does a statistical problem, is it a statistical problem only that falls underneath these statistical engineering case studies? With that, I'd like to conclude and offer these questions for our panelists.
Thank you, Will and Dennis. We will we will hold questions until the panel discussion. First discussant is Marcus Perry. Dr. Perry is a professor of statistics in the Department of Information Systems, Statistics, and Management Science at the University of Alabama's Culverhouse College of Business. He received his MS degree in Manufacturing Systems at Southern Illinois University in 2000 and his PhD in Industrial Engineering from Florida State University in 2004. His research interests include all aspects of quality engineering, with primary emphasis on statistical process monitoring and engineering experiments. Dr. Perry currently serves as editor-in-chief of Quality Engineering, an official journal of the American Society for Quality. Welcome, Marcus.
Thank you, Jennifer. Thank you, Caleb. Thank you, Will and Dennis, for the great presentations. I'll start off by just saying that, I think to sort of address one of the questions that that Dennis had, I do believe that's the discipline of statistical engineering has a lot to learn from other disciplines. Certainly, industrial engineering is one of them. In fact, I believe in the 2012 Quality Engineering Special Issue on statistical engineering, it was Pete Parker that first drew on the similarities between systems engineering and statistical engineering. But if you recall from last year's ISEA Summit, it was Jeroen de Maas that actually drew on similarities between statistical engineering and design science. And I think we have a lot to learn from design science, and this sort of prefaces my discussion today, which you see the title here is Statistical Engineering and Wicked Problems. And so throughout both presentations this morning, we constantly hear large, complex, unstructured problems, but something that's been in me since the last summit was, how do we really define a complex problem? And if you really, you might do an initial Google search, as Caleb indicates, that's what we do as sort of our initial approach. But if a simple Google search yields quite a bit. Here's three definitions here. Complex problems are often defined as those that include the ability to approach them from multiple, perhaps competing perspectives, and which may have multiple possible solutions. Makes sense, pretty complex. Complex problems are problems that are beyond the scope of any single organization to understand and respond to. There's often disagreement about the cause of the problems and how to address them, and the problems can only be addressed and not completely solved. Okay, some of you may agree with that definition based on your experiences. A third definition, complex problems are difficult to formulate. Aha, we're getting somewhere. Because different people will have differing opinions about the cause, nature, and the extent of the problem. It's often the social complexity, something that I didn't hear in some of the previous talks, rather than the technical complexity that makes complex problems so difficult to address. So this got me wondering even more. I started to think, is there a formal sort of I guess, theory? And it turns out there is a formal theory. It's called the theory of wicked problems. back in 1973 by Rattel and Weber. And more formally, what this means is that problems can be generally categorized as either tame problems or wicked problems. And what I think I'm seeing on, and of course I don't know for sure because I don't have the experience, but what I think I'm seeing from the last two slide sets is sort of tame problems, in the sense that there is a definitive formulation of the problem, right? So here we define, in fact, Riddle and Weber define this as tame problems have a definitive formulation, that is one that is exhaustive or contains all the information needed to understand the problem. Okay, and consequently, with tame problems, the problem solving framework tends to be linear. Understand the problem. Once we understand the problem, then we can solve the problem. And I think there's a number of problem solving frameworks that are linear like that in nature, right? That can be used to formulate or provide structure to the problem solving process. However, Riddle and Weber, they continue on and say, well, wicked problems do not have a definitive formulation. That's actually the first property of a wicked problem. That is, the information needed to understand the problem depends upon one's idea for solving it. So we sort of have this non-linear sort of problem solving framework that is needed. Okay, and so I state here that Riddle and Weber, they posit 10 properties of wicked problems, and I have them listed here. I'm not going to go through every one. I'll talk, we'll go through, but we won't go through any detail. But I do provide some detail in there as well. But I will say that if you want a better read, this McCall and Burge paper is a good read, and they actually go through and sort of rethink these properties, and then they provide some suggested modifications to some of the wordings of the properties. And I believe that the McCall and Burge is more from an engineering sort of perspective. Okay, so here's the 10 properties, and notice the very first property of a wicked problem. A wicked problem is one that has no definitive formulation. The information needed to understand the problem depends upon one's idea for solving it. Right. So this is what makes this a non-linear. This is what makes wicked problems require the need for sort of a non-linear problem-solving framework. I'm not going to go through others. I'm just going to point out one. You guys can read through these slides if you want a copy. I'll send them to you in addition to any of the papers that are here. But the other one that I want to point out here, because I'm going to make a point here in a minute, is that number one, there's no definitive formulation of a wicked problem. And then number three, I want to comment on too, solutions to wicked problems are not true or false, but rather they're good or bad. Okay. And again, there's others, and you may recognize some of these as being associated with some of the problems you solve. You may disagree with some of these. These are not my properties. These are properties that Riddle and Weber have suggested are indicators of, in fact, a wicked problem. Okay. The bottom line, as you read through these, you may see that the world is full of wicked problems and just clumsy solutions to those wicked problems. Okay. The next question, and I think this is where we can sort of relate SE discipline to what really ends up being design science in a lot of ways, is how do we address wicked problems? And so I'm using the term wicked problem to imply a complex problem. Okay, a problem that has a definitive formulation, although is a challenging problem, it's not necessarily by definition per se a complex problem, or definitely not by definition a wicked problem, according to Riddle and Weber. So notice the similarities, though, to statistical engineering in terms of what the recommendation is to addressing these problems. Riddle concluded that wicked problems require an argumentative approach to finding solution. And then views solution as a collaborative process. Okay, it's a collaborative process, and it must be. Moore in 2011 suggests the key, and I give these references in the slides here. The key to effective approaches to tackling wicked problems is creating a shared understanding between the stakeholders about the problem and shared commitment to the possible solutions. Now, there's a whole other special issue of quality engineering that talks about collaboration, and I don't recall exactly what year, but it's within the last few years. But that entire special issue hits upon this stuff that we're talking about now. So this does not necessarily mean that there is a complete agreement about the nature of the problem, but that the stakeholders understand each other's positions well enough to have intelligent dialogue. Okay? And you can also see another reference to Conklin. Notice that what I'm not talking about here a lot is statistics. Now, the statistics comes into play absolutely, because it turns out that many of these properties of wicked problems, the problem is the rationale, in essence, for each of these properties relates to cause and effect and trying to determine cause and effect relationships. So, but I'm almost forced to take a broader view of statistical engineering based upon what the claim that statistical engineering is. That is that it is a holistic approach to solving large, complex, unstructured problems. Here's another thing I found. So, how do we address wicked, another way to address wicked problems? The Australian Public Service Commission in 2007 suggested responding to wicked problems require the following. Notice in many of these, you can see a similarity to statistical engineering. Holistic. Some question I might have, though, philosophically speaking, is this, and we'll talk about that in a minute, in terms of the compatibility between SE and wicked problems. Okay, but holistic, certainly. Innovative and flexible approaches. Okay, comprehensive focus. Look at this. Accepting a need for long-term focus, sustainable solutions. Okay, so there is a lot of similarities between what is currently known, what is currently called statistical engineering, and those proposed or recommended strategies for solving, or at least addressing, wicked problems. Now, the first question, so this leads us to the question, is statistical engineering compatible with the theory of wicked problems? And I would say at first glance, I would say yes. There's a couple of problems that I see, and we'll discuss those here. But at first glance, I would say yes, right? And there's evidence of this all the way back in 2012 in the Quality Engineering special issue on statistical engineering, where Pete Parker says a critical function of SE is the active collaborative role in defining the strategic objectives, namely defining the right questions. Precisely. Okay, there needs to be a consensus on what are the right questions, and all stakeholders need to be involved in that. However, there may be some discrepancies. So if we take a look at these two properties that I just, I laid out 10 of them, but I'm just going to look at these two. Property one, the theory of wicked problems implies solutions cannot be assessed through a linear design process or a linear problem-solving framework. That is, we do not have the information a priori to formulate the problem, right? And the only time a linear problem-solving framework would work is if I had all of the information a priori, and we don't have that. So the question that I might pose here is there a discrepancy involving SE's proposed phases in addressing these kinds of problems? So here's the framework, right, that is proposed by Roger and Ron, Roger Hurl and Ron Snee. And the question I would have, is this a linear process? If it is a linear process, then it seems that it would be, at least according to the theory of wicked problems, it seems that it would be limiting in solving complex problems, right? Unless you want to define complex problem, something different, but I haven't seen a definition of complex problems formally in the literature, but I have seen a formal definition under the theory of wicked problems under the theory of wicked problems. So this is one potential discrepancy, and I haven't spent enough time to really look into it, but it was just a question that I had regarding philosophical differences. Property three. The theory of wicked problems claims that judgments of solutions to wicked problems are value judgments, not factual judgments, right? And so much of this likely comes from the social complexities, but what this means is that the Riddle and Weber article also claims that property of three cannot be a scientific process. This also seems to be somewhat of a discrepancy, since the claim of the SE community is that SE is built upon the scientific method. So I'm not saying these are discrepancies, but I think that there's opportunities to look into sort of the procedures and the proposals for addressing wicked problems and how it relates to and how it's compatible with the tenets of statistical engineering. So a basic tenet of SE is that it involves finding solutions to complex problems. And so my point is that complex problems are most often wicked problems, in the sense that there's no definitive problem formulation. And my view is that the SE discipline would benefit significantly by assessing the compatibility of SE as it currently stands relative to, say, the theory of wicked problems. This could identifying these compatibilities and these incompatibilities between the two could identify opportunities to either further define, or even refine the SE discipline. So I'll just leave you with a final point. Is the formulation of the SE discipline a wicked problem? That's all I have.
Thank you, Marcus. Our next discussant is Murat Testik. Murat Testik is a professor and chair of the Industrial Engineering Department at Hacettepe University. He received his PhD in Industrial Engineering from Arizona State University. His research interests and publications are mainly in the area of quality engineering and data mining, with a focus on real-world applications. Dr. Testik is currently the president of the European Network for Business and Industrial Statistics. He is the past editor-in-chief of the Quality Engineering Journal and currently serves as an associate editor for the Institute of Industrial and Systems Engineers, Transactions on Healthcare Systems Engineering. Welcome, Murat.
Thank you, Jennifer. Do you hear me well?
Yes.
Okay. Thank you again. I congratulate the speakers for their interesting, thought-provoking, and insightful discussion on statistical engineering. And also, I appreciate the opportunity to discuss and provide my insights on the topic. I will confine my discussion to engineering of data-driven solutions to complex problems. To state from the beginning, I consider statistical engineering a new emerging discipline. Of course, there are many challenges for statistical engineering to be accepted and to develop as a new discipline. However, as the earlier engineering disciplines, as well as the newer engineering disciplines, which can be considered as specialties of the earlier ones, statistical engineering is emerging based on the needs accompanying the developments. To me, statistical engineering is needed to put statistics in use under the large and complex problems of today's massive data-driven world. Let me argue my thoughts on why this new discipline is not science but engineering. Also, why there's a need to combine the two words, statistics and engineering, to form the label statistical engineering. Engineering and science are different disciplines that have distinguishing characteristics. Science is concerned with discovering basic knowledge, while engineering is concerned with the application of scientific knowledge to solution of problems. Consequently, engineering needs the discovered knowledge from science to put this to use. Certainly, these have developed in parallel and complemented each other. However, developments in science and engineering were not always at the same pace. Engineering aspects of statistics lagged, maybe because it was possible to have the same person be the scientist as well as the engineer. The one who quests for basic knowledge can also be the one who puts it into use. Furthermore, some engineering accomplishments involve an impressive application of fundamental knowledge. Nevertheless, as the problems get larger and more complex, separation of the tasks becomes crucial. I say that problems get larger and more complex. However, I do not necessarily imply that we are having bigger problems today than ever. This may simply be due to having new resources, say computing resources as well as massive and complex data, to tackle the same old problems in a different way, of course, to have better solutions. The distinguishing characteristic of engineering is that engineers design systems so that an engineering process may involve analysis or synthesis. Sometimes engineers decompose, say, an existing system into parts And sometimes parts are combined into a whole, say, a new system. This is often to have satisfactory, better, or alternative solutions to some problems. I'm not saying the best solution here, since our decisions are often rationally bounded in practice. So why not we have statistical engineers design data-driven systems for analysis and synthesis of complex problems? Greater part of the development in engineering prior to the 19th century had to deal with the physical phenomena, later on chemical, electrical, industrial, environmental, etc. The core engineering disciplines that emerged before the World War I are civil, mechanical, chemical, electrical, and industrial engineering. Following the Second World War, newer engineering disciplines such as nuclear, electronics, or aeronautical, environmental, and computer engineering emerged. These are sometimes considered as specialties within earlier engineering disciplines. Either specialties or not, engineering disciplines evolved as a response to developing needs, definitely after a significant body of knowledge is associated with them. So we can consider industrial engineering discipline. With the Industrial Revolution, there was a rapid emergence of industrial organizations, and the size and complexity of manufacturing units, say manufacturing systems, dramatically increased. Over the progression, it is noticed that earlier practices of managing small workshops did not work well for the large and complex manufacturing systems. Work methods and workplaces needed to be designed, and this led to the emergence of earlier scientific management, which is later called the industrial engineering. In this digital age, we are talking more and more about the fourth industrial revolution. Whatever we call it, it's clear that the data are doing the revolution by attacking from abundant data sources to give information. Today, engineering of data-driven solutions to complex problems of organizations is more than a necessity, and I think that statistical engineering will collaborate very well with the industrial engineering discipline, as it was with the operations research, which considerably influenced the development of industrial engineering by impact of analysis approach. These are my thoughts. Jennifer, thank you very much for inviting me.
Thank you, Murat. Our next discussant is Xavier Tort. Xavier Tort is full professor of industrial statistics and quality at the Politecnica University of Catalana, Barcelona, and develops his teaching, research, and consulting activities at the Barcelona Industrial Engineering School. He holds a BA and a PhD in industrial engineering from UPC and an MS in statistics from the University of Wisconsin-Madison. His primary areas of interest are quality improvement, Six Sigma, experimental design, and quality management. Dr. Tort is a past president of the European Network for Business and Industrial Statistics. Welcome, Xavier.
Thank you very much, and good morning and good afternoon to Europeans. I'll try to be very brief and to really comment on what the speakers have said so far. So in the first talk, Caleb and Lindsay basically talked about two issues. The first one is the position of statistical engineering with respect to statistics. And by extension, I think with mathematics and applied statistics and science and engineering. And at the end, they reached the conclusion that a good solution for statistical engineering is to split statistics into science and engineering. I think it's a good, I basically agree. I think it's an appealing solution. As they said, this conflicts with the actual statistical engineering definition. It's true. And just I like the spirit of the definition they propose. saying that is the systematic integration of statistical concepts and methods in developing tools to solve data problems, okay, across a wide range of industries. Of course, this needs but the spirit, I think, is right. I like the idea that it is wider than the one that we have right now, in the sense of avoiding the large, complex, and structured problems. In my experience in explaining what statistical engineering is here in Spain, and by extension, I think in the south of Europe, this sounds a little bit like something for big multinationals far away from SMEs. And I don't like that. I think that we should land this down. And also, I think that it narrows the field to data-related problems or something like that, which I like, because well, as somebody that has spent many years on the quality area, and I think that a problem or part of the blame for quality becoming out of fashion, in spite of the fact that it's as needed as ever, or even more, is that 20 years ago or 25 years ago, it seemed that quality wanted to occupy the area of everybody. So everything was quality, and everything was quality management, and then became excellence and all that. So I think that this idea of being wanting to tackle all sorts of problems, I think it is not a good idea. I think it's not a good practice. In fact, if we look at this statistical engineering definition that in fact is the informs definition, I like it, and I felt really I didn't know it, and I felt really, oh my God, this is what I would like to see, or closer to what I would like to see as a statistical engineering definition. And I thank William and Dennis for providing this. I like very much the idea of talking about challenges and opportunities. I think this is much better than talking about problems. This definition also has this wider sense, but at the same time avoids the large and complex, and so it somehow also restricts the field. In fact, I think that I was so shocked by this definition, and I felt that somebody had invaded our field, and I didn't like that. So, and probably we statisticians have been passive, while many other areas have been invading our fields. So maybe we should sort of try to reorganize our forces and concentrate that statistical engineering more into statistics than trying to expand it and invade other areas. Well, I have said that I don't like the idea of complex problems, but also I have to say that this future of jobs report from the World Economic Forum puts complex problem solving as #1 skill for many years. So I don't know, I might be wrong. But if we change the definition, that means that we will have to change also the vision associated with it. So in my thinking, this is good. I mean, we will change the vision in a good way, concentrating on our field, and which is important enough, and not trying to occupy too much non-statistical ground. I could talk quite a lot about that, relating it with the phases and with our book of knowledge, and it's clearly based, biased towards the statistical area, and we have a hole in other areas that we are saying that are important in statistical engineering. So anyway, there are some cons. It will generate confusion. It may conflict with part of the good and hard work done, and so complex problems is a skill on high demand. But maybe we can follow a sequential strategy and move a little bit towards this, concentrating our forces. That would be my proposal. Well, with respect to these other relevant disciplines, Caleb Caleb and Lindsay say that put this dilemma between, or dichotomy between, consolidation or collaboration. Of course, collaboration is the answer. I mean, consolidation would be more of this invading or trying to occupy too much ground and so on. And William and Dennis, they say we are not alone. And yeah, it's true. I mean, we are not alone. And so we need to collaborate with these communities. This is something very much needed. We need to get people from other areas on board. We are basically something that has been developed by statisticians, from statisticians, and what is more, to statisticians. And at the end of his talk, Dennis said, well, should we train statisticians or people from other areas? And that's a very good question. I mean, maybe we need to think really, if what we are trying to do is something that should be done by somebody else, to train statisticians into some other skills that they don't have. And maybe we should train in statistics people that have these other skills. I don't know, but it's something like that. Okay. We need to think about the customers. I mean, what to whom do we want to sell statistical engineers? To managers? We want to with respect to companies, we want to train statisticians on statistical engineering, or we want to train non-statisticians. So that's something that we really need to define and to be clear about. Finally, Dennis finished his presentation with this, whether the questions, whether the solution should be based on existing theory or following the 6 phases. Well, that's fine. But what I like very much is this idea of a classification of statistical problems. I think that this should be part of statistical engineering. We talk about these similarities between chemistry, chemical engineering, statistics, statistical engineering. Well, chemical engineering uses very much these parts, and we don't have this very clear taxonomy. I like it in this last ISEA webinar, Marco Rey's talk, that he really presented 3 different problems that could be solved using statistical engineering, and there are others. Years ago, there was this nice article by the guys in Waterloo that about robust design. And I think that this should be part of statistical engineering too, to classify problems and to provide sort of general standard solutions for these problems that then so okay, I could talk longer, but I think that we're really out of time, so that's basically my presentation. Thank you.
Thank you, Xavier. So now that we're going to begin the panel discussion, I'd like to start by giving Caleb, Will, and Dennis a chance to respond to what the panelists have said. So Caleb, did you have anything you wanted to say?
Maybe a little bit. So I definitely liked what Marcus said on the wicked problems. That's something I'd never heard of before. So that was interesting to see this classification of problems that it does sound a lot similar to what ISEA is trying to do, or at least the problems they're trying to solve. And so I guess there was a lot of overlap. So all that insight into the exact nature of it, it almost feels like you might get caught in a logical loop, because if you get to a point where you find this complex problem and then you finally nail it down, well, according to the points, it's no longer a wicked problem. So I just thought that was pretty interesting. And then to Xavier's points, sorry, just brain lost it there for a second, but I thought there were a lot of good points there. So this idea of statistical engineering being developed by statisticians for statisticians, and currently 2 statisticians. Yeah, I definitely see that as happening now. It's something that kind of would keep coming up in my discussions with my wife, is that we have statisticians coming up with this, so they're going to approach it from a statistics perspective. So everything that's been set up currently is from that perspective. And so to me, it's beneficial to have people like my wife who understands enough but is outside of the field to provide feedback, to say, I know she looks at this new field creation as like, this is just a big project that so we need to lay out plans and such. But definitely this idea, we need to be reaching out more to people outside of statistics. And I know that's one of the things that they've been trying to do at the ISEA seminars, is bring in other people. But I know early on it was just kind of more on bringing in people to talk on maybe how statistical engineers might relate to managers and such, how that works. But I definitely agree, maybe we need to keep going further. That idea of talking with, what do people expect from statisticians? What are people expecting from this field? What are they expecting? And from outside of statistics, we've Will and David's talk, or Dennis's, sorry, they hinted at that these other organizations exist. So definitely being able to talk with them to get input on things. There was the idea of collaboration versus consolidation. We presented as both options. Obviously, I definitely lean the collaboration angle. I believe that's kind of the intent of the field kind of coming in. So, and again, agree that's definitely something that we need to do. And so again, going to the idea of reaching out, we definitely need to improve upon that, being able to reach out beyond just our local area. I know that's kind of where we've started, but I think that's definitely an emphasis we need to have. I think that's all the comments I currently have.
Okay, thank you, Caleb. Will and Dennis?
Do you want to start off, Dennis?
Sure. So yeah, I thank you to the discussants. I found a lot of those comments very interesting, and this idea of wicked problems was also very interesting. And I think I agree with some of it, Caleb. But at some point, a wicked problem no longer becomes wicked. Once you put the framework and you begin walking down this path of solution. And those were thoughts I had about this idea of complex unstructured problems, as ISEA currently defines it, as at some point the problem doesn't be, at some point it's no longer unstructured, and at some point it's no longer, well, it could still be complex, but it becomes structured at some point. And then at that point, is it no longer a statistical engineering problem? Just very interesting thought exercises there. I believe, I might push back a little bit on whether statistical engineering problems are or are not wicked problems, in the sense that I think we are faced a lot of times with where our solution is based on, our problem definition does depend on the solution, because we don't necessarily know what we're measuring. We think about some of these problems that involve, improving or optimizing. What are you optimizing, or what are you improving, and how do you know you've improved until you define what you're going to improve? And I think I spend a lot of conversations with that. I'm working on a project now that we're talking about developing methodologies for optimizing mass spectrometry for fire debris analysis. Well, what does it mean to have an optimized mass spec? We're spending a lot of time trying to figure that out. Jump over to Xavier and his points. I very much appreciated them. This idea of consolidation versus collaboration. I agree, collaboration, getting involved with these other organizations, I think could be a huge benefit to ISEA. Caleb had a really nice slide that I really appreciated. It was slide number 20, where he used this word consolidation, and he kind of put statistical engineering over top of some of these other disciplines. And I didn't necessarily see that as a bad thing. I don't know that I see it as consolidation so much as collaboration, but I see statistical engineering as laying over, this foundation of what is a structured way to approach these problems in all of these domains, using all of these techniques to solve them. And I think we could, again, that slide number 20 of Caleb's was very impressive to me. I guess I'll end here with this idea of, what is the statistical problem, and do we want to limit statistical engineering to only statistical problems? And Will and I have had a lot of conversations on what a statistical problem is as we are developing this content. We talked about the stochastic nature of so many of the problems in our world. It's easy to see how any problem could be labeled a statistical problem. The UPS problem you might think of it as an operations research problem, but we don't know what package is going to show up on our loading dock the next day. So in that sense, are we dealing with a statistical problem where we don't know what the traffic patterns are going to be on any given day? We need to make predictions. We need to leverage statistical tools. So in that sense, can we label all problems or many data-related problems as statistical problems? And coming back to another comment that Caleb made, was this idea of terming this, rather than statistical engineering, kind of putting this very polarizing label on this, but this idea of analytical engineering was very appealing to me as well, because we are solving problems and we may be leveraging all different tools, not just statistical tools. In that regard, I'm going to push a little bit towards, we have some of these communities already developed, like Informs, where perhaps ISEA can make a large impact. And I don't know, I'll offer the idea of ISEA as a society within Informs, and being able to reach all of these different disciplines that are already existing and are already well oiled in that regard. So with that, Will, I'll hand it over to you.
Okay, thanks, Dennis. I agree with lots of things that you said there. Essentially everything, I think. I'll just mention that a theme I think I heard in all the discussions, which I appreciate very much, is that statistical engineering, as we have defined it now, and as ISEA seems to be supporting it and promoting it, it does seem to be broad, or require a broader view and go beyond the purely statistical. And I think that's a good thing as well. A place where we may have a little bit of disagreement, though, is how good an idea is that? I do see I think there was some very clarifying structure put over it that will help us decide, but I don't think we totally agree yet on which is the best solution. And it'll be interesting to see how that plays out. And then I guess I want to just remind us too, it's easy for us all to get hung up on certain phrases and ideas. I know I do this all the time. So in thinking about large, complex, unstructured problems, it's nice. We like to make things binary. It's either large, complex, and unstructured, or it's not. But it is a spectrum always, right? And so maybe we need to bring that spectrum back and then say, well, here's the part of the spectrum where statistical engineering can really work. And here's a part where it's, it's so large and complex and unstructured and wicked that maybe, we are beyond statistical engineering in some sense, and maybe there's just more societal values need to sort it out. I think that's it. Thanks.
Thank you, Will. Sherry, do we have some questions from the audience?
We have quite a number of questions or comments, mostly comments that came in. So I think I'm just going to pick out a couple of them. And if I don't read yours, they will all get passed on to the group for further discussion. But one of them, Jonathan Smith Renshaw mentioned the question to answer is, what complex problem could ISEA solve that Informs and IISE could not solve? If there's a gap, then ISEA has a role to fill there. So I think that's kind of a nice comment. Here's one. Teddy Cotter sent in quite a number of comments, so I'm just going to read this last one. The systems engineering V model approach to engineering systems is mostly qualitative. Statistical engineering has the potential to incorporate the hierarchical, quantitative variance components of variety and random variation. Yeah, comment that the word engineer is highly regulated in many countries, so we do have to be careful in using it. Wicked problems seem similar to the distinction of puzzles and mysteries that Christine Anderson Cook described in the November 2020 issue of Quality Progress. Puzzles are problems with fixed answers that emerged after all the relevant pieces of information are found and combined. Mysteries do not have clean, definitive answers that depend on perspectives and interpretation of facts by the problem solvers. Understanding the distinction between puzzles and mysteries can drive better collaboration towards the solution to large, complex, unstructured problems. That comment came from Melvin Alexander. Okay, so with that, I think I will stop and just send it back to Jennifer and any of the other people on the line who wish to make further comments.
So it's sort of in a similar line as one of the comments that you mentioned. I think Will and Dennis, in your talk, you really talk about how the Institute for Industrial and Systems Engineers and Informs really do have similar objectives to ISEA. So what do you see as differentiating statistical engineering from industrial engineering or operations research, and that's also could be open to the entire panel as well.
Sherry, thank you. This is Dennis. I think that in some sense that was exactly our point in our discussion today. Was it is difficult for me to see drastic differences. I see these organizations as solving types of problems that are interesting to ISEA, and I am like Caleb said, I remain confused. I spent a lot of time thinking about what statistical engineering is and what the mission is, and I would love to hear from others who perhaps can distinguish and point out differences between what ISEA or the Institute for Industrial and Systems Engineering, how they are different from ISEA.
Hi, this is Xavier. I don't have an answer to this question, but I think that part of the problem is this thing that different fields try to occupy the space of other fields, and I think that Informs, which is my understanding is that it was originally an operation research society, has been invading part of our field. And I think that if we widen the definition of statistical engineering to be a little bit more general and include what we may say in other, not only problem solving, or that depends on what we understand by problem solving, but we include this applied statistics in a more general way. We can sort of define a ground field of our own where problem solving, I prefer to talk about opportunities, but never mind, would also be an important part of this ground field. But I think that this would be a way to really define some borders and define ourselves.
Okay. Yeah, I have been thinking about this for a while, and like, to me, industrial engineering is mostly operations research and statistics, or lots of statistics courses are taught. But when we teach industrial engineering, like we teach one-step solutions. Like, we have examples, textbook examples. You have a question, you have one-step solution. Like, you get the solution to a problem in one step. Like, you do regression, okay, you have the answer. You do design of experiments, even though we say that this is a sequential process, we teach design of experiments by a single experiment. We analyze the results, that's it. But in real world, the idea is that the problems are more complex. You cannot solve a problem in one step. You may sometimes use different approaches. You obtain some information, use it sequentially for another step. So I think that is the place where we have the statistical engineering, and that's what I understand from complex problems. Is not the problem does not have a single one-step solution. So in industrial engineering curriculum, the statistical engineering can have one track as the operations research. To me, when we say operations research, is the deterministic part. We have the numbers given. We don't have randomness most often. But for the statistics, we have the randomness. So we have two components. One is the deterministic part. The other one is the stochastic. Of course, we have the human factors engineering, or ergonomics, or production systems, those kind of things. But those are generally one-step things. But in industrial engineering, for example, we teach 2 semesters of statistics, like one semester for statistics, 1 semester for probability. Then we have simulation, we have queuing systems. We have design of experiments, regression, some electives, and some mandatory courses. So we have lots of components, statistics components in industrial engineering curriculum. Again, to me, we teach everything that is solvable in one step, and that's from the textbooks that we use, because it's how we can do that. We generally teach the tools, but the problems are often complex. So that's what I think that's the differentiating part of the things. Thank you.
Thank you. Would anyone else on the panel like to comment?
Yeah, sure. I'll comment if that's okay. I guess thinking and hearing what all has been said, so I definitely found it interesting in Will and Dennis's. I apologize for keep messing up the name. So Will and Dennis's talk was definitely seeing that similarity between the neighbor disciplines and statistical engineering, and then hearing some of the comment from the panelists. So as I said, I kind of lean the collaboration end, but I definitely see, at least when I look at it, it kind of reminds me initially of when data science came out. My initial view on it was, when I heard data science, like, okay, you just redefined statistics, you gave it a new catchy name. To me, there seemed so much overlap between the two, and I think now I understand the subtle differences between them, but I still see a lot of overlap. The same is kind of, I feel like, with a lot of these other disciplines, there seems to be a lot of overlap. There are subtle differences maybe in the tools that are used. So we in statistical engineering, we have more statistical tools that account for uncertainty. These other disciplines come from more mathematical backgrounds, so more mathematical modeling, more deterministic type approach. It's again that idea of some have advantages in some areas, some not so much in others. So it's this idea that there's definitely a lot of that similarity, I guess. And there's been some kind of terminology going around of, these other fields might be invading our space, or we might be invading their space if we get too large. I worry about that type of terminology, mainly because the way I kind of see it, yeah, there's a lot of people who, it seems like, reinvent the wheel. They're trying to address the same problems, and because these fields may not be aware of each other, this problem presents itself, it needs to be solved, so you're going to try and come up with a solution to it using the tools you have. And so what might feel like you're invading our space might just be we're picking up the slack because you weren't around. You didn't know this was happening. So these were the tools we created to solve the problem, and you can come along and say, well, hey, this is how we approach it. So I guess it's more of this idea of, I acknowledge that there's a lot of overlap in these disciplines, which would lead someone to kind of think of the consolidation approach. And again, I do kind of like that idea because I see a lot of the overlap. So I kind of see it as long-term, something like that happening. Maybe it's more of this idea of the collaboration leading into that. As we work with these other disciplines, the idea is we're sharing tools, and so they will have tools that we weren't aware of. We have tools that they weren't aware of. So I see we're kind of wrapping up here, so I'll try and wrap up my comments pretty quick. Yeah, I guess I see it more as the collaboration is kind of that first step. And then maybe ultimately that might help down the line with some consolidation, whatever that might look like.
Thank you, Caleb. So once again, I'd just like to thank our speakers and our panelists who have really put a lot of thought into this topic, and also to thank everyone for attending today.